So now we are going to discuss about beams. Beam is one of the main topic in mechanical engineering and especially in structural mechanics. So without beams we cannot do any structure and we cannot build any structure. So analysis of beams are very important. So we'll discuss about beam and in the beam we'll discuss about shear force and bending moment diagram. So normally what is beam? So beam is a structural member which is beam is a structural member comparatively larger compared with lateral dimensions. It looks like this. So we all know what is beam. So it is lengthwise it is larger than its cross-sectional dimensions like breadth and width, and loads will be acting transverse to its longitudinal axis. And all these things we are combined together we say as beam. And in the beam we'll going to say about shear force and bending moment diagrams, how we can construct shear force diagram and bending moment diagram. And before going to that, we'll see what are types of beams and what are types of loads. And types of beams we have is cantilever beam, simply supported beam, overhang beam, fixed beam and continuous beams. So cantilever beam, we know that one end is fixed and the other end is free. And simply supported beam, both the ends are hinged or we have supports. And overhang beam, beyond its support there will be some portion of the beam will be hanging over. And fixed beam, both the ends are fixed. And continuous beam we have more than two supports, whereas simply supported beam we have only two supports at both the ends, whereas continuous beams we have more than two supports apart from at both the extreme ends. And type of loads, point load, assume as load will be acting at a single point. It is denoted as W and unit for that load is Newton. And uniformly distributed load will be distributed along the length of the beam in such a manner that the rate of loading will be uniform along the length of the beam. It will be distributed uniformly. And for uniformly varying load, it will be distributed uniformly along the length of the beam in such a manner that the load will be varying from point to point. And from this we'll see what is shear force and bending moment diagrams. Shear force is nothing but the algebraic sum of the vertical forces acting along the length of the beam either to the left or right of the section. And bending moment will be the moments of all the forces acting along the length of the beam. And how to construct shear force diagram and bending moment diagram. And shear force diagram shows how the shear force will vary along the length of the beam. And bending moment diagram will be shows the variation of bending moment along the length of the beam. And we'll take a few examples from simply supported beam. Is denoted as SSB with point load. And for this beam we'll see how we are going to construct a shear force diagram and bending moment diagram. So before going to this we should know the sign conventions of shear force and bending moment. If you take section of the beam, if the load acts upward direction to the left or downward direction to the right, we'll take this positive shear force or positive sign to the shear force. Or otherwise, if the load acts downward direction to the left or upward direction to the right, we'll take this negative sign for shear force. Same way for bending moment. If the load acts along the section of the beam, if the beam bends like this, we have concavity on the top and convexity in the bottom, which is positive bending moment or sagging bending moment. Otherwise, if the beam bends like this, the concavity in the bottom and convexity in the top, we say is hogging bending moment or negative sign for the bending moment. And we'll start with simply supported beam with the shear force and bending moment diagram. We'll take a small beam. We'll construct shear force and bending moment diagram. We'll take simply supported beam. We have supports at both A and B ends. Length of the beam assume as L, and we have load at the middle point. We are assuming load will be acting at the midpoint of beam. assume this is L by 2. And for shear force, we have to consider only the vertical forces. Only the vertical force we have to consider to construct shear force and shear force diagram. Let RA will be the reaction at point A and RB will be the reaction at point B. Now if we take moment about point A, we have RB into length equal to W into L by 2. So we'll have RB is equal to W by 2. This is symmetrical beam, so RA also will be equal. So RA and RB equal to W by 2. From this we'll construct shear force. So shear force will start from point A. So at point A we have vertical force. Already I said shear force will be, it's nothing but vertical forces along the length of the beam. So shear force at point A is RA, and the force acting upward direction towards the left, so FA will be plus RA, that RA will be plus W by 2. So this load will be continuous till the next point. Say this is point C, so this will continue point C. So at point A and point C we have only W by 2. Then at point C, so along with this W by 2, it reduces to W. So minus W by 2. That will continue till point B. So now we have shear force, we have point A is W by 2, point C is minus W by 2, and point B again minus W by 2. By using these values, we have to construct shear force diagram. And initially you just draw a basic line just below the beam diagram, and positive values just plot above the diagram, above the baseline, and negative values just plot below the baseline. And point A we have plus RA plus W by 2, just mark here, and that will continue till point C. So just draw a horizontal line till the next point, and at point C the plus W by 2 reduces to minus W by 2, and we have this, and this minus W by 2 will continue till point B. And if you add this plus W by 2 and minus, the algebraic sum of these two will be our magnitude of load value at that particular point. Then we'll come to bending moment. So bending moment at point A, again we'll start from point A. Bending moment at point A is equal to 0. Moment is nothing but load into distance. So initially we have point load at point A, there is no distance, so moment will be equal to 0. Then move to point C. So moment about point C, here we have RA value, this point C we have L by 2. So this is W by 2. So moment about point C, W by 2 into L by 2. So we'll get WL by 4. So at this point we have moment is WL by 4. Then moment about point point B, we have from point A plus W by 2 into L minus W into L by 2 will get 0. So by using these values we'll draw bending moment diagram. Moment A at point A is equal to 0, at point B equal to 0, at point C we have maximum bending moment, that is WL by 4. And here also we have to plot positive values above the baseline and negative values below the baseline. Just draw the basic line, just extend all the points, mark the points A, B and C. At point A we have 0 bending moment, and point B we have again 0 bending moment, and point C we have WL by 4. Then join this by straight line, because that is straight line equation. Join this by straight line, this bending moment diagram and shear force diagram.